the composition of functions. The easiest way to explain this is to think of it as a double substitution. So we're going to take one, we're going to substitute it into one function, and then we're going to take that and substitute it into the other function. So, for example, when a pebble is dropped in a pool of water, ripples in the shapes of circles form on the surface of the water. The radius of the outer ripple is given by the formula r equals 0.3 t, where r is the radius in meters and t is the time in seconds after the pebble hits the water. If the area of the circle is pi r squared, how can I use my knowledge of what the radius is from the outer ripple formula to figure out what the area would be of the circular ripple after t seconds? So I've got this first formula where r equals 0.3 t. And then I've got a second formula, a equals pi r squared. So really what the question is asking me is, can I figure out the area of the circle as a function of time instead of as given the radius? Can I figure out the area of the circle given the time that has elapsed since I've thrown the pebble into the water? Well, I can by replacing r with what? 0.3 t, and then squaring it. So if I square 0.3, what do I get? Not 0.9, 0.09. So that constant 0.09 goes first, times pi t squared. So now if you were asked, this is every time. Now if you were asked what is the area of the circle after 3 seconds, I can use this formula. So rather than having to put 3 into here and then put the radius into there, I can put 3 into this new equation that I've created. That's what you're doing with a composition function. So if we look at the 2012 Toyota Camry, has a fuel efficiency of approximately 8.2 liters per 100 kilometers, which means for every 100 kilometers I drive, I'm burning approximately 8.2 liters of fuel. The cost of gasoline was $1.25 per liter. So really what we're going to do is we're going to combine functions to get to the point where we can figure out what the cost of gasoline is per kilometer driven, or as a function of the distance driven. So what we're going to start off with is the volume of liters of fuel that can be written as a function of the distance traveled. So it says complete the following for L in terms of D. So what do I know? I know that for every 100 kilometers, I burn 8.2 liters of fuel. So how much would that be per kilometer? Instead of every 100 kilometers, how can I find out how much fuel I burn every kilometer? What would I do? Divide by 100. So 8.2 divided by 100 would be 0.082 times D for distance. So if I drove 100 kilometers, I get 8.2 liters. If I drove 10 kilometers, I'd have 0.82 liters. If I drove 200 kilometers, I can substitute the distance in and figure out the amount of fuel I've used. The cost of gasoline can be written as a function of the amount of liters burnt, or liters used. Complete the following for C in terms of L. Well, I know that gasoline is $1.25 per liter. So how can I use that knowledge to come up with the equation? So if I put in 100 liters, how much will it cost me? How'd you get 125? Times by 100. So I take the number of liters that I've used and multiply it by $1.25. So I get $1.25 L. Now we want to find out the cost of gas in terms of the distance traveled by combining the two functions. So if I notice cost is written as $1.25 times L, and L is written as 0.082 times D. So if I take the equation that I developed for L and substitute it into this equation, I now have an equation that is only in terms of D. So if I take $1.25 and I multiply it by 0.082, what do I get? So what that means is if I drove 50 kilometers, if I substitute 50 into this equation, I would get what it would cost me, which would be $51.25, I think, something like that. If I drove 100 kilometers, I can multiply this by 100, and I would determine, oh no, not 50, it should be $5. What's Yeah, $5 and 12.5 cents. If I drove 100 kilometers, it would cost me $10.25 to drive that 100 kilometers. Okay? So why is knowing the cost per kilometer driven useful? Why do you want to know that?
On a budget.
If you're on a budget, because you can sometimes control how far you drive. If you are, so if we think of some of the occupations in this area, if you're a contract operator or you're kind of a service company to oil and gas, sometimes you might charge your mileage. Well, how do you figure out what you're charging per kilometer? Part of that is you figure out what is it costing you for fuel per kilometer, and then you need a buffer in there to account for your insurance and to account for maintenance. Okay? So the government, when they come out with because the government has a schedule or they have a set amount of what they allow you to charge per kilometer for claiming on expenses for medical and for other travel on your income tax, the amount that they come up with takes this into mind. It takes in the cost of gas and then what insurance or what maintenance would be on your vehicle. So when two functions are combined in this manner, we say that the new function is a composition of the other two functions. So consider the function given by h of x equals 2x plus 3. I can think of this as being composed of two functions. The first function is take x, multiply it by 2. That gives me 2x. Then I take that function of 2x and I add 3. So there's my composite function. So the composite function h says first multiply by 2 and then add 3. So if I look at the map, the function f applied to x maps to 2x. So I can say that f of x is equal to 2 times x. And then the function applied to g gives me 2x plus 3. So g of 2x equals the x plus 3. So it means I take that function of g and I add 3 to it. So if I replace a for 2x, we can write that g of a equals a plus 3, so that g of x would equal x plus 3. So f of x equals 2x, g of x equals x plus 3. And h of x is the composite of that. So h of x says take the g of x function and substitute 2x into it. So if I substitute 2x where I see x, there's my composite function. So again, think double substitution. When we write a composite function, we can say that h of x was the composition of g of f of x. Because I had g of x, which was x plus 3. That was my g of x. And then what I did is I substituted 2x in for that. So I took g of 2x, and 2x was f of x. So there's my g of f of x. When h of x is written as g of f of x, the function f is applied first and g is applied second. H of x is commonly referred to or commonly used for notation as a function of a function. Okay? And class example number 1 and the warm-up number 4, so what we will look at, are useful for those of you that are going to be taking calculus because it talks about the chain rule. There we go. So if we look at class example number 1, consider the composite function h of x equals x squared minus 2. It says, describe in words 2 operations in order which can be applied to x in order to end up with x minus 2. So think if I start off with x, what would I have to do to x to get to this x squared minus 2? Square x. And what else? And subtract 2. So in an arrow diagram, what it means is I take x and I square it. So I get x squared, and then I subtract 2. So if I'm talking about f of x and I'm squaring it, there's my x squared. And g of x squared becomes x squared minus 2. So g of x, so remember this x squared was f of x. So g of x would equal f of x minus 2. And well, that kind of makes a circular argument. Sorry. In terms of x itself, if I was to write an equation so that when I substituted x squared into that equation, I would start off with x minus 2. Because then when I put the x squared into that equation, then I get my x squared minus 2. So if I look at class example number 4, consider the composite function h of x equals x plus 4 all raised to the power of 3. What operations would need to be done to this function to get to x plus 4 cubed? Okay, and is that the order I would have to do it in? Yes. And what tells me I have to do it in that order? The brackets. So the brackets tell me that I would have to add 4 and then cube it. So if I start off with x, I'm going to add 4. So then I get x plus 4. So then my f of x function would be x plus 4. And then I take x plus 4 and I cube it. And that's how I get my x plus 4 raised to the power of 3. So down here, this would be g of x plus 4 would give me x plus 4 cubed. And if this was g of x, so instead of an x plus 4, if I had just an x, I would have x cubed. So it says developing a method for the composition of two functions. Consider two functions f of x equals 3x and g of x equals x minus 5. Complete the diagram to determine a formula for the composite function. So I take x and I multiply it by 3, and that's how I get my 3x. So where I see f of x, I can substitute in 3x. And then I would subtract 5. And there's my 3x minus 5. So g of 3x would be 3x minus 5. So it says use a similar technique to determine a formula for the composite function k, which is f of g of x. So g of x was subtracting by 5. So that means that I start off with my x, and I'm going to subtract 5. That's what happens with g. So that's going to give me x minus 5. And then the next thing that I would do, which is f tells me to multiply by 3. So I'm going to get 3 times x minus 5, which would equal what would I get? 3x minus 15. Okay. Most of the questions, or pretty much all of the questions that you get, are going to be with the examples that we start next. Very few questions we get actually have this chain rule to them, because the questions that we have don't necessarily need the chain. Calculus needs the chain because of the type of equations that you're using. Okay? So what we can do as a flow chart says consider the composite function g of f of x. This little o here is the same thing. It means g of f of x. Where f of x and g of x are given, this is the procedure. So you start with g of f of x. You replace f of x with the formula that you were given for f, and then you apply the formula for g. Write it in simplest form. So if I look at class example number 3, given that f of x equals 10x plus 1 and g of x equals 2x minus 5, complete the work below to determine the composite g of f of x. So I start off with g of f of x. Then where I see f of x, I replace it with the formula. G of 10x plus 1, because that's what f of x is. Then I take this 10x plus 1 and I substitute it into my g of x formula. So where I see x in g of x, I now write in 10x plus 1. So that's my g of x formula with the f formula substituted in. Simplify by removing the brackets. And I get 20x minus 2 minus 5, or 20x minus 7. Or sorry, what did I do wrong here? Oh, plus 2, there we go. My brain still figures it's like a holiday. There we go, 2x minus 3. So I'll do gloss example 4a, and then I'll give you a moment to do 4b. So g of f of x, g of f of x, means this would be g of 2x squared minus 1. That's my f of x. So I substitute that into the g of x formula, and I would have 3 times 2x squared minus 1 minus 4. Remove the brackets. 6x squared minus 3 minus 4 for a final answer of 6x squared minus 7. So now you guys can try B. So this one means g of x. So where I see the g of x inside the brackets, I would replace it with 3x minus 4. And then I would take this function here and replace it in for x in the g of x. So 3 times 3x minus 4 minus 4. So 9x minus 12 minus 4, and I would have 9x minus 16. Starting to become clearer? Okay. So domain and range. In a nutshell, when I'm doing the domain and the range of a composite function, it is not going to be the same as the two functions. Or it could be, but it might not be. So you have to look at each function. So it says, consider the functions f of x equals x squared minus 3 and g of x equals the square root of x minus 1. Without finding a formula for f of g of x or g of f of x, evaluate the following. So f of g of 2 means this. F of g of 2. So that means take 2 and substitute it into the g of x formula. So that would be the square root of 2 minus 1. So what is the square root of 2 minus 1? 1. So then I would get f of 1. And then I would substitute it into my 1 squared minus 3 formula. And what would I get? Negative 2. So what I would like you to do is I'd like you to do the next 3. So if I look at f of g of 0, it means I substitute 0 into here. So I get f of the square root of 0 minus 1. What's 0 minus 1? Negative 1. Can I take the square root of a negative 1? No, so this becomes undefined. Okay? Does it feel good when you know when you got it right? Okay, so now if I look at g of f of 2, that means I substitute 2 into this formula. So I would get g of 2 squared minus 3. What's 2 squared? And 4 minus 3? So now I'd have g of 1, which then would become the square root of 1 minus 1, which is 0. Okay? And finally, g of f of 0 means that I would put 0 in for f, so I would get 0 squared minus 3, which is negative 3. And then I put it into my g formula. I get negative 3 minus 1, which is, and what is the square root of negative 4? Undefined. So it says state the, and we'll look at the rest of this tomorrow. So we'll look at the domains and the ranges of f and g. So when looking at the domains and ranges of these two functions that we were given, x squared minus 3 and g of x equals the square root of x minus 1, what can you tell me about the domain of f?
Well, I know that it's XER because that's what you had on the paper.
Okay, but how do I know that it can be anything? Is there anything that it can't be?
No.
No. When you're looking for a restriction in a domain, you're looking to see if it has a denominator, because I know I can't divide by 0, and if it has a square root, because I can't take the square root of a negative number. Really, those are the only places that you actually have restrictions. There might be certain values that it can't be, such as in a quadratic, because I've got that curve, it can't be certain values that aren't within that curved area. But really what I'm looking for is there possible restrictions? So the domain of f would be that f could be an element of the real numbers. So then if I look at the function of g, are there values that g can't equal? Can it equal 1?
Yeah.
Yes.
It can be less than 1.
It can't be anything less than 1 because then I'm going to get a negative. So it has to be x values such that x is greater than or equal to 1. So now if I think of the ranges, those are my y values. So given that x can be any value, in that quadratic, can y be any value? So in this parabola, does it open up or down? Up, because it's got a positive x squared. And where's its minimum point going to be? Negative 3, because its vertex is going to be a 0 and negative 3. So it's going to be any value greater than negative 3. So the range is y values such that y is greater than or equal to negative 3. And then if I look at my g values, what were you asking, Rachel?
Nothing. I was just talking about y-intercepts.
Okay. It's not necessarily the y-intercept. I have to think of where the vertex would be in this graph. In this graph, the vertex is at 0 and negative 3. And I could get that from graphing it. If I go to the range of g, I have restrictions. So if I look at what my restrictions are, x has to be greater than 1. If I put 1 into this equation, what do I get? 0. The square root of 0 is 0. If I put 2 into this equation, 2 minus 1, square root of 1 is 1. If I put 5 into this equation, 5 minus 1 is, square root of 4 is 2. So my numbers are starting at 0 and getting bigger. So then my range of values for g is a set of y values such that y is greater than or equal to 0. So in order to determine the domain and range of the composite functions, Aaron found expressions for f of g of x and g of f of x.
It's like Aaron.
There we go. and used his graphing calculator to sketch the graph of the composite functions, and he obtained the following graphs. So if I look at his first graph, he gets this linear function and concludes that the domain for this linear function has to be greater than, or sorry, not greater than, has to be an element of the real number system for both of them. And then in the second graph, the g of f of x, he determined that the domain has to be less than -2 or greater than +2, and that the range is greater than or equal to 1. But there's errors in his thinking. So the errors where we have to start back from is we have to go back to what are the composite functions. So if I find expressions for f of g of x, so that would be f of the square root of x minus 1, which would then be the square root of x minus 1 squared minus 3. When I square the square root, it cancels out because it's an inverse function. So I get x minus 1, oops, not comma, x minus 1 minus 3, which is x minus 4. But, what do I have right here? I have this square root. And in this square root, I have a restriction. X has to be greater than 1. So my expression is x minus 4, but my x values have to be greater than 1, because if they're not, when I go back to the start of the question, I would get a restricted value. Okay? Does that make sense for this one? So then if I look at g of f of x, that would be g of x squared minus 3. So if I put that into my square root, I get x squared minus 3 minus 1. So I would get the square root of x squared minus 4. So if I look at this function right here, there were no restrictions on it, but now I check the final function and I look, are there restrictions on that? Well, if x is less than 2, so if it's 1, I'm going to get a negative. So x has to be greater than those 2 values. But if x is less than a -2, I'd get a -3 squared, which would be a +9, or a -4 squared, which would be a +16. So there's my x is less than -2. Does that clear up that part of the understanding? So then if I look back onto the equations, the f of g of x has that restriction where x has to be greater than or equal to 1. So when x is equal to 1, I get 1 minus 4, which is -3. So my equation starts at 1 and -3 and then gets greater. So it's not a full linear function because I have that restriction. So the domain is the set of x values, or actually we'll write it in interval, -1, or sorry, not -1, +1, to infinity. And then my y values are starting at -3 to infinity. And that becomes my domain. So now if I look at this function, this is the function, the square root of x squared minus 4, and when he put it onto the graphing calculator, it gave him this shape here. But if I put in that 2 value, if I put 2 into this equation, what do I get? 0. So really, I should have a point on the x-axis at 2. If x equals -2, what would I get? 0 again. So there should be another point on the x-axis right here. And then from there, if I were to pick other values, such as when x is equal to 3, or say if we did 4. 4 squared is 16, minus 4 is 12, the square root of 12 is 3 point something, I'm going to get a higher value. So I'm going to get lines, they still have that curve, but unlike Aaron's graphing calculator, they actually start at 0. And if I was to look at that calculator and press zoom decimal, it would focus in and you would actually see it touching the x-axis. It's just sometimes given the values and given the dimensions, the ratio aspects of the screen, it makes it look different. So you always have to go back to that function and to those restrictions and ask whether or not this is making sense. So what the purpose of all of that information was to point out the following notes on the next page. When we have a composite function, there could be restrictions on the domain. The restrictions on the domain might have come from the original function, or they might come from the new function. So in the second example with that g of f of x, the restrictions came from that x, the square root of x squared minus 4, not from the originals. It came from that new one. Whereas in the first one, with the x minus 4, the restrictions actually came from the original composite function, or the original functions. In most cases, the domain and the range of the composite are going to be different than the original. In most cases. Now, with that said, there's always probably a case that you can find where they're not, where they are the same each time. However, the domain of a composite function, f of g, cannot be more than the domain of g. So if I have a restriction on g, I'm going to have a restriction on the composite. And that was that first example. Because my restriction on g was that x had to be greater than 1, I have to have a restriction on the composite function. If the range of the composite function can't be more than the range of f. So in the previous example, the range of f was that f had to be greater than or equal to -3, which means when I put it together, that range can't extend below -3. When I create that composite function, there is no way it's going to extend below -3. And it didn't. When x equals 1, I get -3. And everything has to be bigger than -1. So the domain connects itself to g, and the range connects itself to f when it's written in that f of g of x. So if I had it written as f of, or sorry, the other way around. If I had it written as g of f of x, then the domain would be whatever, or restricted to whatever f is. So it couldn't be bigger than f, and the range couldn't be bigger than g. So the domain is the first, the inside, and the range is the outside.